Hi everyone, I will solve GATE 2011 Aerospace Engineering question number 37. Which of the following Airy stress function could satisfy the given boundary condition, assuming constant value of sigma xx equal to p, sigma yy equal to q, and tau xy equal to r along the boundary. This is the figure. There are two stresses, normal stresses, sigma xx. This is sigma xx, and this is sigma yy, and this is tau xy. So we have to find which is the Airy stress function. So this problem is related to stress and strain. To know more about it, you can refer to this NPTEL lecture. First, we will see what are the equilibrium equations for stresses in 3D. So this is the equation for stresses in 3D. So this term is for stresses, shear stresses. This term is for body forces, and this is for mass into acceleration. So this is the net force sigma A equal to m. From this you can get this equilibrium equation. So why we can write these as a three equation, which is dou sigma 11 upon dou x1 plus dou sigma 12 upon dou x2 plus dou sigma 13 upon dou x3 plus rho fx equal to rho x. This is for x. This is for x direction. This is for y direction, and this is for z direction. In this sigma 1, 2 or sigma 1, 3, first one denotes the plane and second one denotes the direction. Like this is the 3D body. This plane is called x, this plane is called 1, this is 2, this is 3. So whatever will be in this direction is x1, this direction is 1, this is 2, and this is 3. So sigma 11 is normal stress on plane 1. Similarly for rest of the stresses. So if there is no acceleration present in the body and there is no body force, then in 2D the component velocity can be written as dou sigma xx upon dou x plus dou xy upon dou y equal to 0. Because in 2D this third equation will not be there. This term will be 0, 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 and these two terms will also be 0. If 1 is written as x and 2 is written as y, and sigma 1 2 equal to sigma 2 1 equal to tau xy. So our equation can be written as dou sigma x upon dou x plus dou tau xy upon dou y equal to 0, and dou sigma yy upon dou y plus dou tau xy upon dou x equal to 0. So it is assumed that a scalar function phi exists, that is a Airy stress function, such that sigma xx equal to dou 2 phi upon dou y square, sigma yy equal to dou 2 phi upon dou x square, and tau xy equal to minus dou 2 phi upon dou xy, dou x, dou y. So if you check, these terms will satisfy these equation automatically. So if this Airy stress function exists, it means if any function phi function satisfying dou 2 4 by del 4 phi equal to 0 is guaranteed to produce stress and strain field that are in equilibrium for an isentropic solid not subjected to bodily forces. If we put it here, this term will be dou q phi upon dou x dou y square, and this term will be minus dou q5 upon dou x dou y square equal to 0. So it will be, it satisfies the equation. Similarly, this also equation is satisfied by these terms. So now we will solve the problem. So in the problem, what is given? Sigma xx equal to p, sigma yy equal to q, and tau xy equal to r. So first we will see this definition of Aerospace function. So sigma xx equal to dou 2 phi y dou y square, sigma yy equal to dou 2 phi y dou x square, and tau xy equal to dou 2 phi y dou x dou y minus. So first we will take this equation and put it here. So put the value of this p, so we will get p equal to dou 2 phi by dou y square. We will integrate this equation one time, so we will get p by plus function of x equal to dou phi by dou y. We will once again integrate this, and we will get phi equal to p y square upon 2 plus fx into y plus some one new function of x. Because this differentiation is with respect to y, that's why this constant will be as a function of x. Now we will differentiate this equation with respect to x. So if we differentiate with this equation with respect to x, we will get dou phi y dou x equal to, this term will be 0. It will be f dash x y plus g dash x. We will differentiate it once again, and we will get dou 2 phi y dou x square equal to f double dash x y plus g double dash x, and this is equal to nothing but q. So if we compare both sides, then we can say that g double dash x equal to q. So after integrating it, we will get g dash x equal to qx plus c1, and g double dash x, gx equal to q x square upon 2 plus c1 x plus c2. So what will be our phi? Phi will be p y square upon 2 plus q x square upon 2 plus f x y plus c1 x plus c2. Now we will differentiate it once again with respect to x. So we will get dou phi by dou x equal to, this term will be 0, this will be qx. This will be qx, this will be f dash x y, and this will be c1 and last term will be 0. We will differentiate with respect to y now. So we will get this term as 0, this term will also be 0, and this will be named as x. So this is dou y dx. So it will be equal to r minus r, because dou 5y 2x dou y equal to minus dou xy, which is minus r. So what will be the fx? Fx will be minus r x plus some constant c3. So our phi will be py square upon 2 plus qx square upon 2 minus rxy plus c1x plus this constant c2 plus c3y plus c2, this one. Now if you see here in this equation, these are all double derivative equation. So our main useful terms will be only terms which contain x square, y square and xy. So these terms we can ignore also. We can take c1, c2 and c3 as 0 also. So if we take all these as 0, then we will get this as the solution. So we have to check which of the option contains all these three terms. So it is py square upon 2 plus qx square upon 2 minus rxy. So only this c contains these three terms. So c is the solution. Thank you.